Okay. So number two says use linear approximation, which is linearization. This is number two on 2.8. To approximate 81.1 square root. And we're going to start with the function f of x equals rad x. And we're going to create a tangent line at x equals 81. We're going to use it to estimate square root of 81.1. All right. So I'm going to stop the share. Okay, I'm going to draw a picture. In fact, I might even go to Desmos here, but I can draw a pretty reasonable picture. The square root function looks something like that. And if this is 81, then the y value is 9. And then, well, I can kind of eyeball in a tangent line. I'll just kind of scribble one in here. Now you'll notice that the tangent line is pretty close to the actual curve. The curve is not very curvy. And that's called local linearity. When you zoom in close enough on any curve, it starts to look less curvy. So the tangent line can actually be used in place of the actual function to do some estimations. So linearization is just really just finding the equation of a tangent line. That's all it is. There's a lot of words out there for it: linearization, linear approximations. Um, um, but it's just basically the same thing. It's basically find the equation of the tangent line. So that's the y equals mx plus b. So I know that the point is 81 and 9. And we choose 81 and 9 because it's a convenient point. The slope I have to find by using the derivative. So I have to take a quick derivative. The derivative of the square root function is 1 over 2 square root x. When I plug in 81, I get 2 over rad 81, which is 2 times 1 over 2 times 9, which is 1 over 18. Okay, so I've got enough information to find the equation of the tangent line. I'll use this famous formula from algebra. Just pop the numbers in. So we got y minus 9 is 1/18, and then x minus 81. And you just do a little simplification. 81 over 18 should be 9 over 2. And if I add 9 to both sides to make it look pretty, um, I get 18 over 2, take away 9, it should be plus 9 over 2. You know what? I'm going to trust myself, so I'm actually going to type it out. The calculator does some tricks. Hold on, give me a second. All right, there we go. So yeah, negative 9 halves plus 9 is, yep, I got it right. All right. Well, there you go. That's kind of 90% of the work right there. We've got what we want. That's the linearization at x equals 81. Now, if I want to estimate square root 81.1, I just simply put in 81.1 into the function, the line, and I just work it out. Now, what I find kind of odd about this one, it just kind of jumps out at me, is that we still need a calculator to work that out. 81.1 divided by 18 plus 9 over 2. And interestingly, my calculator rounded that off. Oops, let me try it again. Oh, there we go. Good. So I'll use the squiggly equals. I get 9.005 and then just fives forever. Dot, dot, dot. Okay, that's the that's the approximation of the square root of 81.1. That's a pretty powerful approximation. That was just by using the line. Now, obviously, in this day and age with calculators, you can actually just punch in the square root of 81.1 and it'll just give you a number. But it's fun to compare how close they are. I'm going to do that real quick. It turns out using a calculator, the square root of 81.1 is actually equal to 9.005555384 dot. And it's interesting that you have to go out 6 decimal places before you get a difference. So the approximation is actually, in this case, accurate out to the 6th decimal place. That's extremely good precision. And it's interesting because you can even calculate like a bigger number, like square root of 83. You could probably do this in your without a calculator. If you plugged in 83 into this, well, I'll use my calculator because it's for time. So the square root of 83, for example, would be, according to the linearization, would be 9.11111 forever. That's the approximation. But if you do it on a calculator that uses, obviously, different algorithms, you still get a pretty darn good answer. And you'll notice that it's at the 3rd decimal place that is where you get a difference. So it's actually accurate out to the thousandths. So it's a pretty powerful little tool to do estimation. And that's kind of the idea. If you go on in math, actually, if you take Calc 2, you'll see what are called Maclaurin series. And those are Maclaurin and Taylor series. Those are actually, you use polynomials to approximate curves. So you're not limited to just lines. And you can actually get even much more powerful approximations. It's pretty cool. Does that make sense what I did there? I mean, feel free to jump in. Anybody got any question? I can go over any step. Can you all see that okay? Okay. No questions on that one. I appreciate that feedback there. Okay, I'll tell you what. Well, I'm going to pause the recording and then
Number 4 from 3.2, maybe.
number 4 from 3.2. Let's take a look. Let me go to it real quick.
Yeah, looking at my homework, I was able to get it correctly, but I remember sort of being confused, and even looking at what I wrote down, looks like I skipped something. I don't know. I just remember them being kind of confusing.
Yeah, this is a famous one. All right, let me share my screen. Here's number 4 from 3.2. Let me copy the main stuff. For each of the given functions, find the derivative f inverse prime at c given at the given point. C theorem, set blah 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 from Stewart's. All right, whatever. So let's take a look at this crazy first one. Let me copy it down. It's f of x equals 6x plus 6x to the 15. C in this case is negative 12. We want to find what a is. And then we want to find what the inverse derivative is at c. So this is a little confusing. I have to admit that the way this problem is phrased is not going to win any awards.
My my big thing is when I look at my homework and I look at the theorem in the book, like they have you substituting f inverse of a into the derivative of the regular f of x. But like
Right.
I never found the inverse function, literally. So how do I know what f
You,
inverse of a
well,
is?
that's the whole point. You don't need to. I think part of what's not made clear here is that, and I will make this clear, is that, you know what? Let me go to my writing screen here. The point on F is AC. Okay, they haven't made that clear. Conversely, the point, I'll say the corresponding point on the inverse graph will be CA.
Okay, so if I solve f of x for c, I would get a.
Yeah, you just kind of swap them. So what you have to do here is, and this function is deliberately chosen to be ridiculous because there's no way in a million years you can actually perform the inverse of this because you're going to have to solve a 15th degree polynomial and it just ain't going to happen. So the idea behind this is to, um, well, not actually perform the inverse, but just kind of use some, I guess you could say, some forensics about how functions behave. And I'll draw a bigger graph here in a moment. And in fact, if we get to it, I'll even go to my website. Or I'll go to the ed discussions because I actually posted something in there I think is helpful. I'm going to ask you guys. This is a case where you just kind of solve it by inspection. In this case, C, even though it's not explicitly stated, C is actually the output of of this function f of x. There's an input that gives you an output of -12. And so what is that input? What is A when you plug it in that gives you -12? And you might be able to just guess it by looking. Anybody have any ideas?
-1.
Exactly. All right. So there you go. So we know. So let's come down here. We know -1 comma -12 is a point on the graph of f. So we know right now we can just go ahead and just swap them. -12, -1 is a point on the graph of f inverse. Okay, that much we can infer. Now we now need the slope. So the question now is the slope at x equals -1 on f. Well, that's not that hard. We just take the derivative. You get 6, and then 15 times 6, which is 90, x to the 14th. Okay. I plug in the -1, and negative, it's actually going to, the 14th power will absorb the negative, so it's just going to be 6 plus 90, so 96. So the slope is 96. Okay. Well, here's the big kind of thing. When you have a graph, and I'll just draw a generic curve like that, its inverse graph will always be reflected across the 45-degree line. So if this is f and this is f inverse, let's say. Now, it may not be actually accurate for this particular graph, but it's general enough. If you have a point AC on the f graph, then take a mirror image, and this point CA is on the point CA is on the inverse graph. Okay. The slope on the f graph, we'll call it M. The corresponding tangent slope is just actually the reciprocal, 1 over M. That's all you need to know. So the slope at, I should say f inverse prime at 96. I'm sorry, my bad, not 96. Let me just rewrite that. My bad. It's f inverse prime at, it was at -12. So -12 gets swapped in now. Well, we already know that the slope is 96 on the f graph, so it's just going to be 1 over 96 on the f inverse graph. And that's it. That's basically, if you just kind of understand the geometry, how they behave when they're reflected, that's all you need to do. I'm going to go out of the screen for a moment and give me a second here. I'm going to go to ed discussions. I have a link in there. Oh, okay. I actually posted this link twice because it came up in two different discussions. All right, I'm going to share my screen. So this question has always been a famous one. It gets asked every semester, so I figured I'd just make up a little document that helps. So hopefully this kind of helps. I made these off of Desmos, so it looks pretty. So it says, this question is causing a lot of, this is over when we used to use inscribe. The graph of a function f and its inverse f inverse are reflected across one another, from one another across the 45-degree line through the origin. So if AB is a point on the graph of f, then BA is a point on the f inverse graph. And if the slope at AB is m on f, then the slope at BA on the f inverse graph is 1 over it, just the reciprocal. So I give you two examples. This first example is easy because it's actually possible to solve for the inverse. You can actually work it out analytically, okay? And you'll notice you can see kind of that nice reflecting going across the 45-degree line. Now I'm going to scroll down and I put this in quotes, of course, hard example. And then again, you look at the example, it's a 21st degree polynomial. These are insane, all right? And this, so we're told that we have a point A comma 65 on the graph. And if you just by look at it carefully, you can see that A would have to be 1. All right, so that's right here. So we know that 1 and 65 is a point on F, hence 65 and 1 down here is a point on the F inverse graph. And by taking the derivative of F, you get this big old number here. You get a slope of 1,265. And so all you need to do then is just reciprocate that. That's all you need to do. So I think it's sometimes easy to get lost in the notation. And I would agree with that. When I looked at that problem in Infinity, even though it's not a bad problem, I think it could have been phrased better. All the right stuff is there, but it's kind of clumsy in the way it's stated. But this is the idea. If you can just remember how the functions relate to one another across the 45-degree line, a lot of it's just kind of done by, I guess you could say, I use the word forensics. You just kind of use clues and just kind of take one clue at a time. All right, I'm going to stop the share on this. Okay. Let me center that. Any questions on this one?
It makes a lot more sense to me now. I kind of forgot that, they're only giving one of the points, but that there's actually A and C. So
Well, it took me a couple moments to read it and figure out that's what they were doing. They weren't very clear that AC is the point. They just simply said, here's C, what's A? And of course, yeah, well, whatever. That's style points.
in general, I find like my instinct a lot of times is to put some of these things in Desmos, but then I feel bad. Like I feel like I should be able to envision all these functions without graphing them. It feels like a crutch or something. How do
Well,
you feel
I
about that?
actually I don't think that's bad at all. I think it's a great idea.
Like I'm actually working on 4.3 right now, which is, concavity and all those things. And when you look at the help in Infinity, they just kind of are like, well, we just know from looking at the equation that it's increasing here and decreasing there.
Yeah.
And I guess you just experience, but
Well, you have to recognize that a lot of people, well, everybody learns slightly differently. Some people are very visual, some people are very analytical, some people are both, some people are neither, I guess. But what they help each other. So, if you can see the graph or you have some sense of what you're supposed to be doing, then hopefully that will help you do your analysis correctly. Or conversely, if you're doing your analysis and then the graph seems to support it, that's good. I totally encourage it. I really don't care how you figure it out as long as you figure it out. And if it takes working, just playing with graphs for at first to get a sense, that's absolutely fine with me. I mean, you have, of course, this day and age, you have access to Desmos and other websites. If this was 25 years ago, you'd be stuck with some lame calculator that could barely graph. You would have to be just totally reliant on the theory. So no, don't feel bad about that at all.
Okay, no, thank you.
Learning is messy. Zoom recording here, 2.5, number 12. All right, we got ourselves a derivative here. It is y equals the quantity 9 plus cos squared of x quantity to the fifth power. These are a lot of these are just good derivative forms to know, especially when we get to the mastery. All right, so let's find the derivative. You actually have nested functions here. You have 9 plus cos squared inside a bigger function, which is basically something to the fifth power. Furthermore, this is actually a nested function. This is actually a cosine within a something to the squared power. So the way you handle it is you just work outside in. And so what you see here is, I'll just verbalize it as something to the fifth power. So you take the derivative of something to the fifth power, you bring down the 5, you copy the something without any changes, and you just reduce the power by 1 to the traditional derivative. And then the chain rule now comes into play. The derivative of 9 is 0. We don't need to write that. The derivative of cos squared. All right, just treat that as its own problem. Pretend everything else doesn't exist for a moment. It's just that. You bring the 2 down in front. It'd be 2, and then actually cos 1 of x, but I'm not going to write the 1. And then, believe it or not, there's another chain. So this is like chain number 1. And this will be chain number 2. And so it's the question now is what's the derivative of cosine? That's negative sine. And you're done. Okay. Now, I would consider that to be reasonably complete. Really, the only thing we can do is maybe bring the constants together. So bringing the negative, the 2, and the 5 is a single constant out in front. But I'm not too picky about that. I think the system would probably accept it. There you go. Does that make sense? Who asked this question? Was this Luis?
Yeah, it makes a little sense.
Okay, which part were you wondering about?
What was that?
Which part were you wondering about?
Well, because I was just having a hard time with I guess knowing when to use the chain rule.
Well, it's
And
all
yeah,
you always use it. It's present in every
yeah.
derivative. Now, in the basic forms, like I'll give you an example of a basic form. Anytime you have a nested function, think chain rule. But technically speaking, that could give you something really easy, like how about just x cubed? All right, believe it or not, the chain rule is present there too. You take the derivative, you bring the 3x squared, but then the chain rule kicks in and you have to take the derivative of that base. Well, the base is just x, the derivative is 1. So you don't need to write that 1. So we don't normally write the 1 in those trivial cases. But technically speaking, the chain rule is present in every derivative.
Okay, thank you.
Sure. By the way, one of the things you're going to see, especially when we start getting integration here real soon, is you'll see functions sometimes written generically like this, like x to the n. And then you'll see y prime equals n x to the n minus 1. And then you'll see it followed by a dx. That dx is technically, it's called the differential, but in this context, it's just simply a little reminder that there's a chain. So
Okay.
x could actually be an expression. It doesn't have to just be x. It could be something more complicated. So that dx is a reminder that you may not be done. You have more work to go.
I don't know if it's going for the differences is often better because with the products, you have the two forms and you can get into situations there.
You know, frankly, L'Hopital's can be kind of a pain in the neck. And so I'll work this one with you guys, show you how to do it, and then I'll give you a general discussion.
Okay, thank you.
Um, this question in particular is a good one because it's actually related to finance vaguely. It's got kind of that future value compound interest formula going. By the way, they spelled it, should be L'Hopital, not La Hospital. All right. To use L'Hopital's rule, you've got to turn it into a product. So what I'm going to do here is I'm going to temporarily call it y equals 1 plus 12 over x quantity to the x over 2. And now I'm going to use the magic of logarithms. And I ln both sides. And the cool thing about that is that the x over 2 comes down in front. Actually, you know what? I said product. And in this case, now let's make it a quotient. Technically, it'll work as a product, but quotient's better. All right, so I brought the x over 2 down, but that's not quite what I want. I mean, it's technically correct. So what I'm going to do next is force it into the bottom by taking its reciprocal. Okay. Now I'm going to verbally just kind of talk myself to the limit here. If I let x go to infinity, 12 over x just gets really small, so I have ln1, which is 0. And then 2 over infinity is essentially 0. So basically, this does satisfy the L'Hopital's conditions. So we differentiate. And we don't use the quotient rule. We just simply differentiate them in place. And it's going to be messy. It's going to be 1 over the quantity 1 plus 12 over x. And then the chain rule, you have to take its derivative. That's going to be negative 12 over x squared. And on the bottom, the derivative is going to be negative 2 over x squared. And I'm using the rule that the derivative of 1 over x is negative 1 over x squared. The negatives cancel. In fact, the x squareds cancel. 12 over 2 makes 6. And so really what I have here is 6 over 1 plus 12 over x. I'll stop here for a second. Did you catch all the magical algebra? Let me know if you.
For the most part, I struggle more with the trig gymnastics than
Okay.
this.
Let's go ahead and finish this one. So when you take, if I take the limit now, I'm going to pop the lim on there. The 12 over x just goes away and you just get 6 over 1 plus 0, which is 6. All right, yay. The problem though is that that's actually ln y equals 6. I'm still in natural logarithm land. So to get rid of that I'm sorry, get rid of the ln and isolate the y, I take base e's of both sides. So the limit is e to the 6. That's the exact answer. Okay. If you are absolutely stumped, let's say you've tried everything under the sun, the algebra's not happening for you, there's nothing wrong with going back to the old tried and true method of just simply plugging that into I guess, Desmos, and then just plugging in big values for x. You'll get a decimal number, but at least you'll get something. And the system usually will accept decimal equivalents. some of those ones where we have differences and we have to turn them into quotients, the algebra can be really, really intense because you have to multiply by their conjugates. And to be honest with you, um, I'm not so sure that's worth the effort. I think sometimes when you just need to find a limit, it's not really a question of style. It's just a question of find the limit. Do whatever you got to do. You got now like 8 different tools to use. So you always have a fallback option. And some of those questions in the, yeah, let's see. So we have one. Can you show us an example that uses Desmos? Yeah, I'll show you a case. In fact, maybe I'll do this one. But yeah, you always have a fallback. So let's go to Desmos. Give me a moment. Uh, got too many things open here. I'm going to, I tell you what, I'll do this one on Desmos, and then maybe I'll pick another one out of the homework and do that on Desmos too. So, all right, I've got it written down. All right, so I'm gonna go to Desmos. Let me share the screen. The way I do it on Desmos is type it in as a function, just like that. Need an interesting graph. Check it out on the left side. Cool. And then let's just say I zoom out. Oh, there we go. All right, cool. You see that leveling off? So if I type in, let's say 10, I get 51.536. If I type in 100, all right, okay, you can see the leveling off. It's going to take a while. Let's type in some big numbers. How about 1,000? 389.27. How about 10,000? 401. How about 100,000? 403. So it's starting to level off. How about a million? 403 again. How about 10 million? It's looking like 403.428. You can see it's kind of locking in. Okay, I think I'm starting to mess it up now. Maybe I went too fast. Hold on, let me try it. Oh, that's weird. I think I may be overloading it. Okay. Well, anyway, but the point is you can see, in fact, I'm gonna go to the third line here. I'm just gonna type in y equals 403.41, and you can see that nice horizontal asymptote effect. That's exactly what you're finding in this case. It's a horizontal asymptote. You all see that? Let me pull another one up. Let me go to, I'm gonna stop the share for a moment. Um, I'm gonna be confusing myself. I'm gonna go to, I'm just gonna pull one off the, let's do a different one. How about number 11? Number 11 is a copy, if you can forget it. It's 15x e to the 1 over x minus 15x. All right, so let's do that. Um, in fact, I'll do that one on Desmos, and then I'll go back and I'll show you some maneuvers analytically. So let me reshare the screen. No, wrong thing. There it is. Okay. All right, so I'm gonna get rid of this, get rid of this, just get rid of all this. So I've got 15x e to the 1 over x minus 15x. That's an interesting graph. I'm gonna have to zoom in to get a sense. Okay. Now the question is asking us as x goes to infinity, and you can clearly see, in fact, I think you might even estimate the answer is probably 15. Um, let's just try some big numbers. How about 100? Okay, 15.07. How about 1,000? 15.007. How about 10,000? Yeah, 15.0007. So it's looking pretty darn promising that the limit is 15. And if I were to type in the line, I get a nice horizontal asymptote there. Isn't that cool? Okay. So this is like the this will always work. This just trying and plugging in numbers to, if you're careful, it should work every time. If you wanted to work this one out analytically, you can factor out the 15x. You get e to the 1 over x minus 1. That's a product. And again, now the 15 is just really going along for the ride. You can pretty much pull it out in front, forget about it until the very end. But you have to force it into a quotient. So I would turn that x and throw it in the bottom this way. And then perform L'Hopital's rule. So you take the derivative, do whatever simplification you need to do, and then it should work out. Okay. In this case, I don't think you need to multiply with a conjugate because we were able to make a quotient out of it with just a couple algebraic maneuvers. And also, I'll just mention, we don't need to do the natural log in this case because in the one up here, there was no way to take that original function and create a quotient out of it without breaking it first. We had to somehow get the exponent out of the perch. But here, we didn't need to do that. It was pretty much good to go. Does that help make sense? Just kind of wrap the show up here. Thank you for attending. I will post this to my video site here by about an hour or so. And hopefully this helps. And in the meantime, just throw them on ed discussions and I'll look at them there. Thank you for attending. Where our test is a week from now. So we'll probably have another one of these next Friday too. So they seem to be pretty fun. All right, you guys, you have a safe night wherever you are, and we'll go ahead and end it. So cheers.